All right, so let's talk about a problem in electrochemistry that's been a real thorn in the side of scientists for, 50 years now? We're going to dive into how new materials form, literally atom by atom, and how a really subtle but super critical flaw in our models was finally figured out. Okay, let's get into it.
What this all boils down to is a massive question for anyone in materials science. How do we actually model, and then predict, and then hopefully control how things get built at the tiniest possible scale? I mean, getting this right is absolutely crucial for everything from building nanostructures with insane precision to creating the next generation of batteries.
The specific process we're really zeroing in on here is called electrochemical phase formation. Think of it as the very first, foundational step. It's how, when you get the electrical conditions just right, atoms floating around in a solution decide to team up on a surface. They form these stable little seeds, or nuclei, and that's what everything else grows from.
Now, for decades, people have been trying to nail down the perfect mathematical model for this whole process, and their efforts have really split into two main schools of thought.
And this really highlights the core dilemma. On one hand, you've got the classical Gibbs model. It's elegant, It uses these big, familiar concepts like surface tension. But you gotta ask, does a concept like surface tension even make sense for a tiny clump of just a few atoms? Then on the other hand, you have the atomistic models. Now, these are way more realistic for those tiny scales, but they rely on these microscopic numbers, like how fast an atom sticks to the cluster, that are just incredibly, incredibly hard to actually measure in a lab. So you're stuck between a simple model that might be wrong and a right model that's basically impossible to prove.
But here's the thing, modeling a single nucleus isn't even the hardest part. The real challenge comes when you have lots of them forming all at once, all competing for the same atoms. That's where it gets messy, and that's where scientists really needed a clever way to simplify things.
To get a handle on this chaos, they came up with this idea of a diffusion zone. You can think of it as a personal little feeding bubble for each growing nucleus. It's the area of the solution that a nucleus is pulling its building blocks from. And as that nucleus gets bigger, its bubble gets bigger too.
And this is where Scharifker and Hills had this honestly brilliant idea back in the 80s. They realized that sure, diffusion to one lonely nucleus is a perfect sphere, but once you get a whole bunch of them on the surface, their little bubbles start bumping into each other and overlapping. And over time, the combined effect isn't a bunch of individual spheres anymore. It's more like a single, flat diffusion wave moving down toward the surface. It was a genius move that turned a complicated 3D problem into a much cleaner 2D one.
It was an amazing idea. Really powerful. But, and there's always a but, hidden inside this beautiful simplification was one critical, unrealistic assumption. And it was an assumption that stuck around in the standard models for decades, causing all sorts of little problems that researchers just couldn't quite explain away.
And here's the problem, spelled out perfectly in this 2009 paper. The issue was the unfeasible consideration of a uniform height for all diffusion zones. Basically, the models were pretending that every single one of those feeding bubbles was exactly the same size, which, of course, they aren't. Okay, so this is the crucial disconnect. The standard model, which is based on this classic theory called KJMA, had to assume all the zones were the same height, just to make the math work. It treated them all as equals. But reality is a lot messier. Nuclei pop up at different times. A nucleus that formed early has had more time to grow, so its diffusion zone is bigger, it's more established. It should win any fight with a younger, smaller neighbor. So how do you fix this? Well, this is where the breakthrough finally happens. Instead of trying to force all the zones to be the same, a new model came along with a simple but really powerful new rule for how they overlap.
The logic here is just so clean and straightforward. It goes like this. Nuclei don't all appear at once. Each one starts growing its own diffusion zone. As these zones get bigger, they start bumping into each other, and when they do, a simple hierarchy kicks in. The older, bigger zone wins. The first one there gets the territory. It's basically first come, first served for building with atoms.
And look, this wasn't just some clever idea scribbled on a napkin. The researchers backed it up with serious Monte Carlo simulations, and the results were clear. This hierarchical model gives a much more accurate, much more robust picture of what's really happening on that surface.
So, great. After a 50-year-long headache, we finally have a model that gets the overlap right. But what does that actually mean for the scientists in the lab using these equations every day? What does this breakthrough really change?
Well, the first result is kind of weird, actually. It turns out that this new, much better model has zero effect on the calculated value for the nucleation rate, the parameter we call A. That number stays exactly the same. So you might be thinking, wait a second, what was the point of all this then?
But here's the punchline. The real prize here is a much more accurate number for n0. That's the number of active sites on the electrode surface. By finally modeling the competition for space correctly, we can get a true count of just how many starting blocks are available for these nuclei to form on.
And that is why this all matters so much. We're finally moving past these unrealistic assumptions and getting a model that actually reflects the real world. Knowing the true number of active sites is everything. If you want to control how a material grows, its texture, its performance, the whole shebang, you have to know your starting points. This new model finally gives us a reliable way to do that.
Which brings us to a final, pretty mind-bending question. For half a century, a tiny flaw in our models was holding us back. Now that this problem is solved, now that we can model the very beginning of creation with so much more accuracy, does this finally open the door to building materials atom by atom with perfect control? That's the dream, and this research just took us a giant step closer. Thanks for watching.